So okay. So I'm going to talk about some problems that are only tangentially. So I know a lot of you are here for the logic program, but I'm sorry, there's going to be very little logic. And well, I mean, not that kind of logic, but yes. So okay. So I'm going to talk about this problem, which is sometimes called Hilbert's 10th problem over Q, because the analogous question with the integers is known to be undecidable. The answer is no. And so, but it's still unknown whether there is an algorithm that would decide, given a multivariable polynomial, whether there's a solution to the equation. And it's very easy to see that this is equivalent to this question phrased in geometric terms about whether you can tell whether a variety has a rational point, meaning a point whose coordinates are all rational numbers. Okay, so let me start by doing a few reductions. So in this, so I'm mostly going to be talking about this problem. So we may assume, first of all, that x is smooth, and the way you reduce to that is so non-singular. That's because if you look at you can sort of stratify by looking at the singular locus, and the singular locus has lower dimension, and so you can do an induction on dimension. So you can use induction on the dimension. Or if you want to say it another way, you could just take the singular locus and then take the singular locus of the singular locus and so on. You get a stratification of the variety, and each difference is smooth. And so if you want to decide okay. You can also easily assume that x is irreducible, because if it's a union of smaller varieties, you can just test whether each one has a rational point. You can also assume that it's geometrically irreducible. So what that means is that it stays irreducible even when you look at it over any field extension, such as if you look at it over the complex numbers, for example. So I mean, the reason that this works is because there's a little proposition that says if you have a smooth, if you already know that your variety is smooth and irreducible, but if it's not geometrically irreducible, so it means that over some extension it breaks up, then it turns out that there cannot be any rational points at all. And so maybe I won't prove it, but let me just show you an example of what this is about. So suppose my variety is just given by this equation. So this is kind of a silly equation to be solving, but okay. So what does it look like? I mean, I guess it's two lines, yeah. But the lines are the x plus y equals square root of 2 and x plus y equals minus square root of 2, and it's pretty obvious that neither of those can have x and y both rational. So and it always looks like this in this setting. It always looks like a variety and together with its Galois conjugates. And then you can't have a rational point there, because then if you applied the Galois automorphism, it would go to a different component, but it's a rational point, so it also stays where it is. And so that doesn't make any sense. Okay. Anyway, so you can assume all this. You can also assume that x is affine, just because if you can choose an open cover and apply and test whether each piece has a rational point. And instead of this, actually, I don't want to assume that. You can also assume that it's projective. Actually, this reduction is a little bit trickier. I mean, for example, you can imagine you have an affine curve and you want to test whether it has a rational point. Okay, you can take a projective closure. So here's your curve. You want to know whether it has a rational point. You can take a projective closure which might add some point at infinity, and you can ask, if you have this algorithm, you can ask, okay, is there a rational point on this projective curve? But maybe the answer is yes, because the rational point is right there. And then you learn nothing about whether there's a rational point on the affine part. So it's actually quite a tricky reduction. So experts can try to think, how do you actually do this reduction? If you know how to decide whether projective varieties have a rational point, how can you figure out whether an affine variety has a rational point? I mean, the key is, in this kind of setting, what you need to do is you need to find a you need to find a higher dimensional variety such that its rational points, it has rational points above all the possible rational points here, but nothing above this one point. And so it's anyway, it's quite tricky to construct that. Yeah, so this reduction was done by Raphael Robinson in one case, and then I generalized it at some point. Yeah, so as I said, so the key is to find a morphism. So well, this certainly suffices. If you can find a morphism of smooth projective varieties, say smooth projective varieties. So let's say x, or let's say y going to P1. That's such that when you take the rational points on y and you push them down by this morphism, you get exactly just the points on the affine line. So there's no point above infinity, but every other fiber, yeah, it's weird. Yeah. So okay, all right. Anyway, so that's okay. So I think I'm done with these reductions, and so let's pretend we're trying to prove a positive answer. So I mean, most of the logicians try to prove negative answers for this kind of thing, but let's pretend we actually want to find an algorithm. What might you try? Yeah. So. Okay, so the first thing you might try, maybe I'll say step 1, is to check. I mean, maybe you get lucky and you first check whether there's a real point. And maybe you're lucky, maybe there are no real points. And I mean, this is a good check to do because first of all, it's known that you can actually do this. So by work, so logicians know about this. So that follows from work of, well, I mean, it's generalizations of the Descartes rule of signs and Sturm sequences and things like this. And in logic terms, it's because there's a quantifier elimination for the real numbers in a certain language. So there's actually an algorithm you can use to test this. And yeah, so for example, I mean, suppose you have a projective curve given by this equation inside P2. I think you can see quite easily that there's no rational solution. Yeah, 0, 0, 0 doesn't count when you're talking about projective space. So yeah, so this has no real point. Yeah, so there's no real point. So therefore no rational point. And and you can do similar things. I mean, in number theory, the real numbers are just one of the possible completions of the rational numbers, and you can also check similarly for using the other completions. So you can check if x has a p-adic point for every p. And this is more or less, I mean, if you don't know what the p-adic numbers are, it more or less amounts to looking at solutions to your equation modulo p squared, modulo p cubed, and so on. And this is a way of it encodes all of those. And again, just as there is for the real numbers, there's an algorithm for any, well, first of all, for any 1p, any 1p, you can check this. But in fact, there's also an algorithm that lets you check all the p's at once. So yeah, so this is all easy. So maybe I'll just do another example here. So if you have, so as I give you this, so this is some genus 1 curve again in P2. Oh yeah, sorry. Okay. Yeah, that's. I mean, I guess. Okay. Anyway, yeah, this is better. Yes. I want it to be smooth. Yeah, sorry. Okay, so this is, so the point here is that you cannot have a non-zero solution to this because at least when these three things, whenever they're non-zero, they have distinct two-adic valuations. So that, in other words, the power of 2 in each of these rational numbers is going to be, they're going to be different because they're different in mod 3. And so there's no way that they can, these numbers cannot be 0. Yeah, so, in terms of two-adic numbers, you would say this has no two-adic point, and hence no rational point. Okay, so these are all basic tests you can do, and there's certain circumstances where just checking these two things is enough. So, for example, there's the Hasse-Minkowski theorem. And this says that if you take if you're looking at a quadratic form, so if for x that's defined by a homogeneous polynomial of degree 2, so in Pn, so this is supposed to be that's a degree 2 homogeneous polynomial. For such a variety, to test whether it has a rational point, it's true if and only if it has a p-adic point for every p. And I should say, when I say every p, I mean, well, I'll write p less than or equal to infinity, where q sub infinity means real numbers. So you should test that as well. Okay, so this actually, so for these kind of varieties, you already know there is an algorithm, because this side you can check. And so then it's interesting to ask then, well, does this hold more generally? Does it hold for all varieties? Because then you would have an algorithm. And well, I guess, as I'm sure many of you know, the answer is no. And so the first counterexamples were, I believe, due to Hasse. Hasse, sometimes that's called the Hasse principle, but he actually disproved his own. He found counterexamples to his own principle. So this can fail. This can fail for more complicated x. And so in particular, it fails, for example, for the norm form equations coming from non-cyclic extensions of Q. So it can fail for more complicated x. And after that, there are many other counterexamples were found. So Lindt and Reichhardt in around 1940, they found examples of genus 1 curves. And then Swinish and Dyer in 1962 found an example of a cubic surface. So like that, except just 1 degree higher, where it fails. Yeah, and all these proofs of the failure, they all looked like ad hoc proofs. Use various clever number theory and use quadratic reciprocity and so on. But then eventually, so a lot of counterexamples, and then finally Manin in 1970, he found a systematic way to explain all these counterexamples that had been found. And so he found that there is one method that explains why these examples don't have rational points. And to do this, he came up with a new kind of obstruction a new way to prove that a variety has no rational point, even when it has p-adic points, local points for every prime p. And so this is called now it's called the Brauer-Manin obstruction. As far as I can tell, Brauer really didn't have much to do with it, except that it uses the Brauer group. But anyway, some people call it the Manin obstruction. Anyway, so let me explain how this works. So first, let me take K to be any field, and I want to consider certain K algebras. They should be finite dimensional as a K vector space, and they should be central algebras and simple K algebras. Okay, so maybe I should say a little bit what these mean. Let's see. Yeah, okay, so central just means the center. This means the center is K. And okay, finite dimensional means as a vector space. Simple means that the only two-sided ideals are the trivial ideals. So there's a zero ideal and the unit ideal, and they should be different. And yeah, okay. So yeah, so for example, yeah, maybe I'll just do some examples for k being the real numbers. So here, so okay, the trivial example is just R itself. That's a one-dimensional central simple algebra. Another example is you could take the quaternion, the ring of quaternions. So that's the non-commutative ring generated by two numbers I and j, satisfying the relations that I squared is -1, j squared is -1, and ij is the anti-commute. Ij is -8ji. So you quotient by the two-sided ideals generated by those, and you get a four-dimensional algebra, and you can check that center is the real numbers, and yeah, and it's a division ring, so there are no non-trivial ideals. There's some other examples also. You could also take n by n matrices, works as well, over the real numbers. That satisfies all these conditions. Or you could also take n by n matrices over with entries in the quaternions. And it turns out that these are all up to isomorphism over the real numbers. And okay, so if you take the set of these, yeah, and you can always do this construction about taking a matrix ring over it. So usually what people do is they mod up by an equivalence relation, where you say that where if you have, I mean, you define A to be equivalent to B if they're both matrix rings over the same division algebra. So for some D and M and positive n and n. Okay, so in this, for the real numbers, this set has two elements, and yeah, and you can also make this into yeah. So this is called the Brauer group, and it's a group. To make it a group, the group law is induced by a tensor product of algebra. So this induces the group law. Okay, so in this case, for the real numbers. Yeah, so for the real numbers, you get the Brauer group. Well, it's a group with two elements, so there are not a whole lot of choices. So I'd like to write this group over 2 like this. Multiples of a half modulo 1. So and yeah, so this is the real numbers of the identity, and this corresponds to a half. And if you tensor H with H, that turns out to be isomorphic to 4x4 matrices over the real numbers. So you can see, well, even if you didn't, yeah, so it's of order 2. Okay, yeah, so you can also, similarly, you can compute the Brauer group of other local fields. For example, it turns out that using local class field theory, the computation, this is go into that, you can prove that for other primes, for other completions, this is Q mod Z. And also from out of the calculations that went into global class field theory, in the early 20th century, there's a description of the Brauer group of Q, and so and it's described by an exact sequence. So it goes like this. Yeah. So first of all, if you have a field extension, then you always have a way to go from the one Brauer group to the larger Brauer group of the larger field, just by tensoring your algebra up to the larger field. And so there's going to be there's a homomorphism like this, and it turns out it lands in the direct sum, and then each of these is contained in Q mod Z, and then you can add up the numbers to get a map to Q mod Z. Okay, so in other words, to specify a central simple or an element of the Brauer group of Q, you just have to specify an element of this for every P, and it should be 0 for most P, because it's a direct sum, and the invariants, you can't just specify them arbitrarily. There's a condition. Their invariants have to add up to 0 in here. So for example, with quaternion algebras, these numbers you get here will always have to be 0 or a half, and so you have to have an even number of them in order for it to actually come from an element of the Brauer group of Q. Okay. so it's because of this condition that not every tuple here comes from here. That's going to be useful in ruling out rational points in some examples. And so I want to explain next an example due to Iskovsky. Okay, so Iskov. I mean, I always worry about spelling these names right, although I guess it's just a transliteration anyway. So I guess I can write whatever I want. Okay, so okay, good. So all right, so let's take X to be. I'm just going to illustrate how the Brauer-Manin obstruction works by showing how it works in a specific example. So let's take the smooth projective model of this surface. So I'm writing down a surface in affine space. So in a surface in A3 with coordinates x, y, z. And you're supposed to take then a projective closure and make it and desingularize it. Okay, so the question is, can you find rational solutions to this equation, or maybe at infinity? Okay, so we're going to prove that the answer is no. That there's, and by the way, you can check. It's easy to see that they're real points. Yeah, you can just choose an x whose square is between 2 and 3, and then you can write that as a sum of two squares. And it's also easy to check using things like Hensel's lemma that there are p-adic points for every p. So that's not going to let you rule out points. So, but nevertheless, we're going to prove that there's no rational point of this. And so, okay, so we're going to do a proof by contradiction. So suppose you do have a rational point on this variety. So how are we going to use the Brauer group to get a contradiction? So I'm going to write down a particular central simple algebra over Q. It'll be like the quaternions, except instead of I squared equals -1, J squared equals -1, and J squared is going to be something else. It's going to be this rational number. So yeah, remember the x0, y0, and z0 are just rational numbers. So this is just some number, and then they still anti-commute. So you can check that this actually defines another 4-dimensional central simple algebra, and so it has some class. It gives you some element of the Brauer group of Q, and now you can check. We can try to calculate what the invariance of this element would be. In other words, what it would map to in that exact sequence there. So you can check, for example, that this class, when you look at it over the real numbers, then it maps to 0 in the Brauer group of R. And the reason, I mean, you can see that directly because if you have a real point on that variety, the value of x squared cannot be more than 3. Because if x squared are more than 3, then the right-hand side would be negative, and then you would have no solution. So it means that this number, whatever it is actually going to be a positive number. And so, but then if you're adjoining a j that satisfies j squared equals a positive number, I mean, you already have a square root of that number in the real numbers. So it's like as if you were adjoining like j squared equals, I don't know, yeah, some number. And so you're making a new square root, and so then you're going to get some zero divisors in this ring because you have like j plus the square root of this or j minus the square root of it. And so that because you have those zero divisors, this quaternion algebra actually ends up being the 2x2 matrix algebra over the real numbers. So that's why it maps to 0. It gives you a trivial algebra. And similarly, you can check that it maps to 0 in the Brauer group of QP for all p not equal to 2. And this is independent of which point you take. It's in other words, this, yeah, so this. On the other hand, if you calculate what happens over in the Brauer group of the last one, in the 2-adic numbers, it turns out you get 1/2, no matter which 2-adic point you take. So now, okay, so why is this a problem? I mean, so there are p-adic points on this for every p, but this tells you that no matter which points you take, they're incompatible, they're incoherent. They don't actually come from a rational point, because the invariance, in order for this to come from a rational point, these numbers would have to add up to 0 in Q mod z, but they don't. No matter which choice of real point, p-adic point They don't add up. Yeah. So this contradicts the exact sequence. And so this proves that there actually is no rational point on this variety. So yeah, so therefore x has no rational point. So, yeah, so this is the kind of thing that this Brauer-Manin obstruction does. It gives you example. Yeah, you have a question?
So is the case that p not equal to 2 just because characteristic 2 is bad, or because we have the x squared minus 2 there?
It has to do with the specifics of this equation.
Okay.
You have to check sort of where the 2-adic points of this lie,
okay.
And then you have to check, yeah, what happens when you take two numbers. I mean, you have to check things like that these numbers don't become 2-adic squares,
Okay.
And things like that to calculate this.
Okay, so this is not a general thing. This
No, it's very particular to this equation,
okay.
And yeah. So, I mean, the fact that how did I know how to write? How did I know how to write this down? Well, I mean, what you can say is that you can actually view this. I mean, if you change this x0 and actually view it as just x, being a rational function on the variety, then you can think of this as being in the Brauer group of the function field of this. And actually, there's a notion of the Brauer group of a variety itself, and actually, you get an element of the Brauer group of x itself, whatever that means. Well, I know what that means, but it's some you can define it using a cohomology. Well, maybe I should have said that. Well, okay, I haven't mentioned any cohomology, but I mean one connection. I mean, why is this called a cohomological obstruction? I mean, one reason is that this Brauer group turns out to be isomorphic to a Galois cohomology group, where you have the absolute Galois group of K acting on the multiplicative group of a separable closure. Yeah. And similarly, you can define the Brauer group of X using étale cohomology instead of Galois cohomology. And yeah, so in general, what happens? Okay, so this is all for that example, but in general, what happens is that each element of the Brauer group of X gives you a potential obstruction to rational points in the same way that this particular element gave an obstruction here. And if you use all the elements of the Brauer group, they cut out a certain locus inside. Oh, I think I forgot to define this as well. Maybe let me just say something about that. Maybe it's just a notation, but so when I write this, it's just a way of packaging together all the p-adic numbers. This is like if you take the product of all the QPs, but then it's traditional to put a condition on it to make this product locally compact. You insist that almost all the coordinates lie in ZP, and then you take the sort of restricted direct product. And then this, to say that this is non-empty is the same as saying that there's a p-adic point for every p. Okay? And then inside here there's and if it's projective, then this is literally just the direct product of all the p-adic points. Okay, but now there's going to be only some tuples in here will be compatible with the Brauer elements in this way that this will show that there's an incompatibility. And so what you get is there's actually, using the Brauer group, it cuts out a certain locus in here where all the rational points must lie. And what happens in some examples is that this, even when there are p-adic points for every p, so this set is non-empty, it can happen that this set is empty. This can be empty even when there are local points at every prime. So even when this is non-empty, and so when this happens, this is what it means to have a Brauer-Manin obstruction, because it means when you have this, then the fact that this is empty means you don't have any rational points. So this is how you can prove that there are no rational points, even when there are p-adic points for every p. Okay, good. So All right, so that's what I wanted to say about the Brauer-Manin obstruction. Now I want to move on to another obstruction, and then at the end I'll talk about whether, if you put all these obstructions together, are they enough to answer those questions? Okay? All right. Are there any questions in the meantime? Okay. Yeah, so maybe I should have said this is almost entirely a historical talk. So there's not much. I'm not really going to spend time talking about some the very, very new results, but actually there are not so many very new results. We're all kind of stuck. So okay, so the descent obstruction is something. I mean, the reason it's called the descent obstruction is because it's related to Fermat's method of infinite descent that he used to prove that certain equations. You probably know about some of these, like x to the fourth plus y to the fourth equals z to the fourth. That he proved that these, to show that certain equations don't have rational solutions. Okay, other than trivial ones. Yeah. So so Chevalier and Weil generalized what Fermat did to finite covers, and then it was generalized by Colliot-Telen and Sans-Souci and then generalized further to non-abelian torsors. Okay, so by Harari and Skorobogatov. Okay, so all right, so let's see. So okay, so here's the idea. So you start with a variety x, and you want to know whether it has rational points. So suppose you can find a bundle over this, so where it's a variety that has an action of some linear algebraic group G. So which could be a finite group, or it could be something like GM or SL2 or something like that, whatever. And okay, so Y I'll draw as some higher dimensional variety, and I want to assume that that this is a G torsor. It's a G torsor over X, or differential geometers would probably call it a G bundle. And so it means, at least geometrically, what this means is that if you look at one of the fibers, each fiber has G acting on it simply transitively. And so so above each point there's a G action. And so you get all these G orbits, each of which looks kind of like G if you choose a base point. And then, or another way is, okay, let's give this morphism a name, so F. Yeah, but there's also see maps of algebraic varieties. And another way to say this is that this is a free action of G on Y, and X is the quotient. So if you take the quotient, then you collapse each of these orbits to a point. Yeah, okay, so given this, there's a way, there's a map where if you take a rational point, it's down here, you can look at its pre-image, so you'll get this F inverse of X, this fiber, and that fiber will have this G action, but it doesn't necessarily have a rational point. But if you choose a point over some extension, then it will look like G acting on itself. But in general, it could be a non-trivial torsor over the field Q, and to classify, those torsors are classified by elements of a Galois cohomology group, H1 of Q, G. And so this is just the map that takes each rational point to the class of its torsor above it. And so maybe as an example, let me just mention one thing. So as a fact that when does X go to the trivial class? Maybe I'll call it 0. That holds if and only if Well, being the trivial class means that there's actually a rational point in the fiber. And so these x's for which you have a rational point in the fiber, that's just the image is of the rational points on y. So it's just like this. And so you can describe all the x's that go to 0 as being just the images of this point. And okay, so you can now try to classify the rational points according to what the fiber above it looks like. And so you have a disjoint union over the possible types, which are the classes in H1 of Q cover G. Yeah, I know I haven't defined what this is, but anyway, there's only so much time. So yeah, but anyway, so you can, and then for each class you can take all the rational points that map to that class, such that the class of that fiber is equal to that sigma. Okay, and then and one of those sets we have a description of. The ones for which, if I take sigma to be a trivial class, I just told you that set is just the images of the rational points from Y. And it turns out that all the other sets in this partition also have nice descriptions. So if you want to decide which rational points map to some other class, some particular class that's not 0, what you can do is you can translate that condition into a condition about some other torsor having a 0 class. What you can do is essentially you take that bundle and you subtract sigma from all the fibers, more or less. And so you get instead of just this original G bundle, you get some other twisted bundles. So for every sigma, you can twist it, get a new variety and a new morphism here. That's going to be some other bundle, and so you'll have a bunch of these. And then you can understand this as being it's the disjoint union now of those sets, and each of those sets is just the ones that come from the rational points on Y. So ultimately, this means that if you want to know the rational points on X, it's enough instead to find the rational points on all of these varieties. Now that might seem like a bad thing to do because you started with the problem of finding rational points on one variety, and now I've replaced this with the problem of finding a rational points on possibly infinitely many varieties of higher dimension. But actually, it actually sometimes is good, because sometimes you're lucky and some of these varieties might fail to have local points. Maybe one of these has no real points and a different one has no two-adic point, even though X has both. And so in that way, sometimes you can rule out the points on X. So yeah, so anyway, you can try to understand this by looking locally. So this will be contained in the union of all the local points on all these. And so this union is yeah. And moreover, what turns out to be the case is that although a priori there are infinitely many sigmas, only finely many of them contribute here. Most of these are empty. This is a version of the fineness of Selmer groups, if you know about this. And so it's what goes into the proof that the elliptic curves, the rational points in the elliptic curve, are finely generated. That, like, for example, things like E of Q mod 2 E of Q, that's a finite group. And so this is actually some finite union. And so actually, you see, it's a little better. So you only have to figure out what the rational points are on finely many of these. Okay, and so, yeah. And so let me give a name to this. Let's call this set. Let's call this X. I mean, it's a subset of X of A, and it'll be the subset cut out by this particular bundle, which I'll label by F. And then you can try to do this not just for this one bundle, but you can try to. I mean, this gives you some restriction on where the rational points of X can lie, because And so you can now try to intersect these for over all the f's and get an even better restriction. So, and this is what's called the descent set. So just as the Brauer set gave a restriction on where the rational points can lie, this gives you another way to get a restriction. So you just take the intersection of all these for all possible algebraic groups G and all possible bundles for those. And so that's, yeah. And you can also define, okay, so that's a nice obstruction. And you can also try to combine these obstructions, because you can do things like, okay, I'll look at all these y's, but then I'll try to check if there's a Brauer-Manin obstruction for each of these. And so there are various combination obstructions you can write down. So I'll just talk about one of them, which is called the Étale-Brauer obstruction, where you don't look, it's a little bit tamer in that you don't look at all algebraic groups. You just look at the finite Étale groups, the finite groups acting. But then so you take G to be finite, and you take all possible f's. But then instead of just taking this set, which was defined to be this union here, you don't just take the union over these sigmas, and you don't just take the local points on these things, but you also apply the Brauer-Manin obstruction to try to make it smaller, and so that cuts it down further. Okay, so all right, so now we have a bunch of obstructions, and I want to say like how in these last few minutes, let me say what these things what we know about them. All right. Okay, and I know I haven't given all the possible definitions, but yeah. Okay, so all right, so here's the whole picture. So okay, so way over here I have the local points on A, and we said, okay, we can define this subset, the Brauer subset, that's guaranteed to contain all the rational points. And we also have, okay, and I guess you will also have the Étale-Brauer set, which is going to be smaller because one of the Étale covers you can take as just X itself, and you're applying a Brauer-Manin obstruction there. But this is possibly stronger, so this is going to be contained in there. And there's also this descent set. And we know that the rational points are contained in all of these. So it's contained in all of these. So, and so now, yeah, and I can tell you various things that are known. Okay, so there's a deep theorem that says that these are actually equal. That even though there are only two, it's kind of like a grand unification of all the obstructions we know about. This one turns out you don't get any. You get the same information from the descent obstruction as you get from applying Brauer-Manin obstruction to these finite covers. And so, yeah, and I should say that, by the way, these two kinds of obstructions I've mentioned, these are almost the only ways known how to prove that a variety has no rational point. I mean, the only other thing besides these is there's a p-adic method called Chabot's method, and there are generalizations of that. But beyond those, that's essentially all that we know how to do. Okay, so let me just maybe I can put a couple of names here. So this equality is due to a work of a bunch of people: R.E., Mikhail Stoll, Alexei Skorbogatov, and Cyril Demarche. So this was, yeah. So this, yeah. And what you can ask in this picture is, so if you know that one of these sets, for each of these sets, you can ask, when you know that it's non-empty, does its non-emptiness imply that X has a rational point? because that's ultimately what we want. We want some kind of test for whether there's a rational point. And so, well, what are the answers here? So here the answer, I mean, if you just know that there is a QP point for every prime P and a real point, I already told you that that's not enough. Okay, so let's see. I guess I'm trying to line up. Okay, this is no, that's due to, that is because of Hasse's counterexamples. Also it's known that the Brauer-Manin obstruction is not enough. That's not the only possible obstruction. There's some cases where this is non-empty. In other words, the Brauer set does not obstruct it, but still there's no rational point. And this was the first example. This is due to Skorbogatov. And maybe you can guess what he did, because in order to prove that the answer is no here, it means the Brauer-Manin obstruction is not enough. So you have to come up with some other way to show that there's no rational point. And so whenever you prove one of these no answers, you're really coming up with a new obstruction to rational points. And so what he did is he calculated that he found a variety for which this was non-empty, but there's so many tall covers where you could show that this is empty. And once you get one of this empty, then there can't be any rational points. So that's what he did. And then later, so it turns out these are also not enough. So this is a result of mine. So maybe I won't try to say what I did now, but I guess in some sense I came up with another obstruction, although it's a little bit related to these. And so so now we're getting desperate because we've run out of obstructions. And so maybe you could try. So I proposed something else you could try. Here this descent obstruction, you as I said, you reduce the problem of trying to find the rational points here to finding the rational points on these more complicated varieties. Finally, many things here. Maybe you could take those, and maybe you can do a descent obstruction on those. Have torsors over these torsors, so like iterated torsors, and maybe you could continue like that. And so that way you can actually define a subset. That's the descent obstruction, where you apply it twice, and then you can do the descent obstruction, and then you can intersect all of those and get the descent to the infinity obstruction. So yeah, see, I don't know how to write. Maybe I'll just call it like that. So, and unfortunately, what happened is that it turns out that these are all equal. So there you don't get. So this is a result of Yang Chao, a fairly recent result that these are all, that you don't get anything new. So okay, so we're all kind of stuck here. So that's where things sort of stand. Maybe I could say, okay, I hate to end on such a pessimistic note. So maybe I can say one more thing. So even though we don't know, by the way, it is expected that all these obstructions are not enough. Beyond, well, I guess we showed that all those are not enough. But even, there are other examples of things where we know that that these obstructions don't tell you anything. For example, if you look at hypersurfaces in projective space, where the hypersurface is 3 dimensions or more than at least 3-dimensional, then it turns out the Brauer group is trivial, it just comes from the Brauer group of the ground field, and also they're simply connected, and there are no interesting torsors either. So the Étal Brauer, all these things there's no obstruction. But on the other hand, there are various various believable conjectures based on heuristics that predict that hypersurfaces of high degree don't really have very many rational points. And most of them probably don't have any at all. So we think that there are lots of examples where there should be some other reason why they don't have rational points, but we don't know how to say it, what it could be. But what might be true, though, is that these obstructions are good enough for large classes of varieties. For example, for all cubic surfaces it's conjectured that the Brauer-Manin obstruction is enough. That if the Brauer set is non-empty for a cubic surface, then there really should be a rational point. And you can do computer experiments with that and so on. And there's a more general conjecture that includes this case of cubic surfaces due to Colliotonen and Saint-Sucre. I mean, they started making this conjecture in the 1970s, and then they started getting, they started thinking, okay, maybe they started becoming more and more ambitious, and they said, okay, maybe it works not just for cubic surfaces, but maybe for all rational surfaces. And later said, oh, maybe it's all rational varieties of any dimension, or there's something even more general, rationally connected varieties. Those are varieties for which every 2 points can be connected by a P1, roughly. And so, yeah, so they conjecture, for example, that if X is, so here's the strongest version of the conjecture, or at least one, yeah. So if X is rationally connected, then if you take this set, not only does this tell you whether there is a rational point or not, but they conjecture that the rational points are dense in there. So in other words, if you have this set and you can, not only can you, if this set is non-empty, you can also, let's say, oh, I not only do I want a rational point, I want a rational point that is in this tiny little real neighborhood. And it's also in this tiny little three-adic neighborhood simultaneously. And as long as those conditions are not obstructed by some Brauer group expression, then the conjecture is that there is a rational point here. And so, yeah, so this is, but this is unknown even for cubic surfaces. So, but I mean, okay, so maybe I'll end on one positive note. So let's pretend this is true. What can you get from this? So one thing that you can deduce from this is a solution to a famous open problem from the 19th century that asks whether every finite group is the Gallo group of some extension of Q, of some Gallo extension of Q for some, yeah, so for some finite Gallo extension. Yeah, so okay, so at least, well, okay, so I don't know whether this conjecture is true, but I think but anyway, it'd be nice if it were, because you would get this. So, all right, so I think I'll end here. So thank you all for your attention.